everybody, Chapter 2, Lesson A on Quadratic Functions. We're going to do a little vocabulary and properties of quadratic functions, graph a few quadratics, look at the advantages of standard factored and vertex form, and then interpret the meaning of the vertex, which is a maximum or a minimum value based on some other attributes of that given quadratic. So let's go ahead and get started. So a polynomial function has this definition: let n be a non-negative integer and a sub n minus 1, all the way down to a sub 2, a sub 1, and of course a sub 0 will be real numbers with a sub n not equal to 0. The function given by f of x below is called a polynomial function in x of degree n. So this would be our leading term. This would be our constant value. So a quadratic, which we're going to talk about today, its leading term would be a sub 2x squared. So this would be the quadratic term, the linear term, the constant term. Notice down here in blue, I've got a quadratic function called L of x. A sub 2, the coefficient of x squared here would be negative 1. Here is n, which is 2. That's our quadratic term. A sub 1 would be 4, and a sub 0 would be negative 11. Okay, you can see here I've got a constant function. This would be a function of degree 0. Okay, a linear function, which would be a function of degree 1. That's its highest powered term. This would be its leading term. The negative 13 would be its leading coefficient. Again, our quadratic L of x, which would be a quadratic function. Leading term, negative x squared. Leading coefficient, negative 1. And then t of x, which is a cubic function. Leading term, 12x cubed. Leading coefficient, 12x. Now notice here, this is a cubic function, but it does not have a linear term. So a sub 1 would be 0, right? Because that linear term no longer exists. So I've got a cubic term, a quadratic term, and then a constant term. Lots of stuff coming on this page here, but I want you to recognize that this in blue is what we're focusing on in this lesson, quadratic functions. So let's specifically get into the quadratic function and its characteristics. The definition of a quadratic function, let a, b, and c equal real numbers with a not equal to 0. The function given below is called a quadratic. So you can see that f of x, he has a leading coefficient of a, its quadratic term, a linear coefficient of b, its linear term, and a constant value of c, its constant term. Some vocabulary and properties of quadratic functions are as follows. Quadratics are also referred to as parabolas and are U-shaped. They either open upward or downward. Quadratics that open upward have the property that a is greater than 0. So you can see I've got a red function here where a is equal to 1, x squared. I've got this purple function here where a is equal to 1/10. So if a is less than 0, like this blue function, where a is negative 1, the curve itself will open downward. Now there should be arrows on the ends of these functions, purple, red, and blue, in order to indicate that the function is continuous and will continue on for all x values. I had cut off this graph, so those aren't present, but you'll notice over here on this blue function, these arrows show you the end behavior. Okay, so let's talk a little bit about some of the properties here. Two specific things that I'd like to focus on are the vertex, which is the minimum value if a is greater than 0. So if the function opens upward, there will logically be a minimum value. We call the coordinates of the vertex h, k, and we'll talk about why we do that later. The axis of symmetry, which is the symmetrical axis, right? It splits the function itself perfectly in half, is given by negative b over 2a. And you might recognize that from the quadratic formula, where you have negative b over 2a in that first part right here. Okay, that is the symmetry line, also called the axis of symmetry. And b and a are the values that we have above in the function. So a is the leading coefficient, b is the coefficient of the linear term. Okay, a couple more items before we get into some other stuff here. Quadratics are symmetrically shaped about their axis of symmetry. Already spoke about that. And the vertex is the location of the minimum output if a is less or greater than 0, or the maximum if a is less than 0. So here's the vertex of the blue function, vertex of the red, vertex of the purple, and then of course vertex of the function we've already looked at. Okay, let's get into some of the inner workings of the quadratic function. So quadratics can be written in 3 separate forms. The first form is standard form. This is probably the most typical form you'll see, hence why it's called standard form. But you'll see it in this quadratic form, quadratic linear constant. This is very helpful when finding the y-intercept. Okay, so if I wanted the y-intercept, I would plug a 0 in for x, and I would get c. So the y-intercept would be the point 0, comma c. Okay, let's look at factored form. Factored form, when put in a form like this, would help us to find the x-intercepts. So in this case, if I wanted to know where g of x equaled 0, it looks like clearly if I were to make this first term equal 0, x would have to equal m, and in the second one, x would have to equal n. So the two x-intercepts would be 0, comma m and 0, comma n. That's helpful in finding the x-intercepts. The third form that we're going to use today is called vertex form. It's put in this form here, and a shows up as a coefficient of this binomial, right? Binomial 2 terms, x minus h. H is some value, right? Some number. So is k. This is a really nice form to work with because the coordinate or ordered pair hk is the vertex coordinate. So if a is greater than 0, we just found the minimum. And if a is less than 0, then we just found the maximum. Vertex form is very powerful and helpful in finding the minimum or maximum value of a quadratic function. Let's go ahead and get into some examples here on the next slide. One more thing that we'd like to be aware of when working with quadratic functions is a thing called pattern of change. Okay, so the typical pattern of change, I'm going to graph this first function, f of x equals x squared. Typical pattern of change is we go over 1, up 1 in both directions. The next one we go over 1, up 3. Oops, I messed that up. Over 1, up 1, 2, 3. So this would be the function. I gotta go over 1, up 1, 2, 3. Good. Talking to myself again. This would be f of x equals x squared. That's the pattern of change when a equals 1. When a equals 2, in the second example, it doubles that pattern of change. So we're still starting at 0, 0, but now we're going to go over 1 and up 1, 2. And then we're going to go over 1 and up 6. Now I'm not going to be able to even see that point on my graph due to the size of the graph that I've written here. But you can see how that would be a vertical stretch. So over 1, up 2. Over another 1, up 6. Over another 1, up 10. Okay. Now, if a was negative 2, that would mean we'd go over and down. So if a is 1/2, that means we'd go over 1, up 1/2, then over another one, up 3/2, over another one, up 5/2, etc. So I'm going to real quick sketch these other blue functions. Let's graph the second function, f of x, and we'll call it f sub 2 of x, and then we'll do f sub 3 of x. Okay, notice that it's still going to open upward. However, we're shifting it down 3 units. So we're going to go down 1, down 2, down 3. Still same pattern of change, over 1, up 1, over 1, up 1, 2, 3. Other direction, over 1, up 1, over 1, up 1, 2, 3. So I'm going to take this function, sketch it through the following points, and it should look almost exactly the same. Well, it should. Human error a little bit. Actually, that looks pretty good. It's been shifted down 3 units. Now notice that would be f sub 2 of x. Now I'm going to flip the graph over and shift it upward 4 units. So here will be its vertex at the point 0, 4. And now instead of going over 1 and up 1, I'm going to go over 1, down 1. And then over 1, down 1, 2, 3. So my graph for f sub 3 of x would look like that. Go the other way, over 1, down 1. Over 1, down 1, 2, 3. Of course, these graphs are always symmetrical. So this would be a graph of f sub 3 of x. Okay, let's sketch the g of x functions. These look like they're in vertex form for us, and I forgot to square that second function. So we've got g of x. Let's sketch g2 of x. Some low-calorie Gatorade. Sorry, I just plugged a name there. Okay, so if I have this function, this tells me the vertex is at the point 3, negative 4. So let's go over 3 and 1, 2, 3, down 1, 2, 3, 4. There's my vertex. So that point would be 3, negative 4. Now I'm going to graph this with an a value of 2. That means over 1, up 1, 2. And left 1, up 1, 2. Now I'm just going to stop there. But I've now stretched this function. It's the same stretch as g of x, but it's a vertical stretch of f of x, right? Okay, let's graph g3 of x. Okay, it's going to be flipped over, so it's going to open downward. I see that a is negative. The vertex is going to be at negative 2, comma, negative 1. So over 2, 1, 2, down 1. There's my vertex. Now, we see that here that a is a negative 2. Therefore, we're going to go over 1 in both directions and down 2. This is our pattern of change. Typically, we ask you to identify at least 3 points on a quadratic, so you would say negative 2, negative 1. This would be the point negative 1, comma, negative 3. And this would be the point negative 3, comma, negative 3. Perfect. Okay, let's graph h of x. This would be a vertical shrink by a factor of 1/2. So let's go. Looks like our vertex will be at the point negative 1, comma, 2. Negative 1, comma, 1, 2. There's the vertex. It's going to open downward. Okay, so what I like to do here typically is, let's see. Instead of going, let's go over 1 in both directions and then down 1/2. Okay, obviously a vertical shrink by a factor of 1/2. Okay, so this point would be 0, comma, 3/2. This would be negative 2 comma 3/2. Okay, there you have it. There's graphing some quadratics. Just paying attention to A. Is A greater than or less than 1? What is the pattern of change? And where is the vertex? So let's go ahead and get into some more stuff with standard and factored form. So here we have standard form. We're going to find the y-intercept as well as the x-intercepts. A synonym for x-intercepts is zeros and roots. So be prepared to find the zeros of the function or find the roots of the function. Those are all synonyms. Okay, then we're going to find the minimum or maximum outputs, which is tied directly to the vertex output, and sketch a graph of the function. So let's first find the y-intercepts. Okay, so y-intercept, let's do in red. If I plugged a 0 in to both functions, in the first I would get 0, -8, and in the second I would get 0, 12. Okay, so yeah, it's going to be a problem unless I make the scale on this graph a little larger. We'll just wait on that. Okay, let's go x-intercepts. Okay, standard form is not our friend for x-intercepts unless we factor. So it looks like I would have an x, oh boy, let's see, plus a 4 and an x minus a 2. 4 and -2 multiplied -8, and they add 2. So it looks like my x-intercepts will be the point 0, -4. Oops, I'm sorry. -4, 0, and 2, 0. Okay, so I'm going to plot those. I'm going to go with a smaller scale here. This will be -4, 0. And this will be, oops, I don't want to put that there because my graph's going to run into it. Just a little forward thinking. And then 2, 0 right here. Okay. It looks like I would have my y-intercept at 0, -8. So where would my minimum value be here? Right? Because A is positive, A is equal to 1. My graph is going to open upward. Okay, where would my minimum value be? Well, it'd be halfway between my x-intercepts. Okay, I could use for my axis of symmetry, I could say that x equals -b, which is -2, over 2a, which is 2 times 1. So that would tell me that my axis of symmetry would be at x equals -1. But x equals -1 is also the average of my x-intercept values, my x's. So this is where the axis of symmetry will lie. So what I want to do is I want to find f of -1. Well, that would be -1 squared plus 2 times -1 minus 8. That's going to be 1 minus 2 minus 8, which will be -9. So it looks like I'm going to have my minimum value at 0. Oops, sorry, that's wrong. At -1, -9. And the sketch of my graph will go through all of these points and make our graph look like a nice, oof, that was brutal. You get the point. Okay, there it is. There's some clean properties using standard form. My dog is drinking water in the background. I apologize. Okay, so let's look at g of x here. Let's find the x-intercepts. That's a good girl. -2x squared minus 2x plus 12. Now when factoring something like this, what I'm going to prefer to do is pull out the leading coefficient. Okay, so that's going to leave us with the following. Oops. I think I screwed something up there in factoring that out. Yep. That should be a negative. Okay, pull that out. That should be a positive x. Oh no, I was right. We're good. Questioning myself. Sometimes you just got to be confident and roll with it, right? So I would have x plus 3, x minus 2. That tells me my x-intercepts are 0, negative 3, and 0, 2. Okay, so let's sketch this. 0, 2. We'll go with a similar scale. Whoops, totally jacked that up. How about negative 3, 0? Some of you probably caught that. And 2, 0. Nice. I messed that one up. Good work. All right, and then negative 3, 0. There we go. Okay, so does this function open up or down? Well, a is negative. A is less than 0. It's negative 2 specifically. So I'm going to open this downward. And that's going to be really ugly because check this out. The y-intercept is 0, 12. Gross. That's off of our current sketch. So I'm going to put it like right here. 0, 12. And the fun thing is when I try to find my axis of symmetry on this one, it's going to be a fraction. Great. X equals negative b. Well, that's going to be negative negative 2. So it's 2 over 2a, which would be negative 4. So x equals negative a half. Great. All right, so it's going to be somewhere in here. I don't know what the output is yet, but I'm just going to sketch it. Oh, gross. That was really poorly sketched. It looks more like a rocket ship now than anything, but that's okay. I'm not going to judge myself, and I won't, I might judge you a little bit, but let's figure out what g of negative 1/2 would be. That's going to be lovely. Okay, so g of negative 1/2 would be negative 2 times negative 1/2 squared minus 2 times negative 1/2 plus 12. This is actually kind of going to come out nicely, or somewhat nicely. This right here is negative 2 times 1/4, which is negative 1/2. And this right here comes out to be 13. That's 13. So that's going to be 12.5. So this will be negative a half and 12.5, so 25 halves. Okay, so it's got a max value on that function at that value. Okay. All right, let's get into some factored form work. Okay, factored form, here we go. Factored form is mostly useful in finding the x-intercepts, so it's pretty much a breeze right away. So I can say my x-intercepts advantage factored form would be 3, 0 and negative 1, 0. Okay, y-intercept, actually not bad either. What do we plug in for the y-intercept for x? Well, what we do is we look for f of 0, which would mean I'd plug a 0 in for both x's, which would mean I'd just have negative 3 times 1. So our y-intercept is negative 3. Okay, well that's not that bad either. Okay, so now I got 3 points. I just don't know that any one of those is located at the vertex. So what I would do, what we just did, is I'd find the axis of symmetry by taking negative b over 2a, but I don't have it in standard form, so I can find negative b over 2a. So there's 2 different ways to do it. You could either take your x-intercepts and average them, and I'll do that right here, or you can use the axis of symmetry, negative b over 2a. So first I'm going to do it using the x-intercepts. I'm going to take 3 plus a negative 1 divide by 2. That's 2 over 2, which means I should get x equals 1 for my axis of symmetry. Okay, I'm going to show you the other way now. If I were to put this into standard form, foiling it, I would get x squared minus 2x minus 3. So the axis of symmetry would be negative b, which would be 2, over 2a, which would be 2 times 1. So either way, I would get x equals 1. Totally up to you how you go about that. I'm going to do a slightly different scale here. Here's my axis of symmetry at x equals 1. I've got x-intercepts at 3 and negative 1. So this will be 3, 0. And this will be negative 1, 0. Okay, graph is opening which way, up or down? Well, I see a positive leading coefficient, and both of these x values are positive. Therefore, it's going to open upward. I'll graph this one in red. No, we'll do blue. No, green. Sorry, getting all crazy. Okay, now let's find that min value. What x value would I plug in to find that min value? Well, I would plug in x equals 1. So f of 1 would be 1 minus 3 times 1 plus 1. F of 1 would equal negative 2 times 2, which is negative 4. So we should get negative 4 for the minimum value. I'm going to do that in, we'll go black. 1, negative 4. And then we sketch the graph. Okay, now something very important to see here is that the vertex, this is something I didn't touch on earlier, is always going to be negative b over 2a, comma, f of negative b over 2a. That's all that I did there. This is negative b over 2a. This is f of negative b over 2a. That'll find you your vertex. And then depending on the orientation of your function, it'll either be a min or a max. In this case, it's a min. Okay, same thing here. Let's breeze through this next one. Oops, x-intercept. The negative 2 does not do anything to the x-intercepts. I would have x-intercepts of negative 1, 0 and 5, 0. Okay, y-intercept, I'm going to plug in a 0. So g of 0 would equal negative 2 times negative 5 times 1. So g of 0 equals positive 10. So the y-intercept is 0, comma 10. All right, I'm going to change my scale slightly here. There's my y-intercept. I've got x-intercepts of negative 1, 0 and 5, 0. I think that's right about here. Ooh, the vertex is going to be way up there, out of my graphical potential. Let's find it anyways. Okay, notice that this function is going to open downward. So I'm going to keep real steep there. It's got to come up and through that y-intercept. I'm going to guess our vertex value would be way up here. We'll figure out what that is in just a minute. Well, that's poor, but okay. Okay, so let's find the axis of symmetry. I'm going to use my method from earlier. I'm going to take my x-intercepts, average the two x values. 5 minus 1 over 2. That's going to equal 2. So our axis of symmetry will be x equals 2. To find my vertex, I got 2 comma g of 2. So let's figure out what g of 2 is. G of 2 will equal negative 2 times negative 3 times 3. Looks like I'm going to get 18. It's way up there. Okay, that might have been a little absurd there, but I would have 2 and 18. And my sketch of my graph clearly here won't be proportional at all, but I didn't plan ahead very well on that example. Okay, that's the use of factored form. I'm now going to get to vertex form and show you how powerful that is. Okay, find the y-intercept, x-intercepts. also known as zeros and roots, minimum or maximum outputs, and sketch a graph of the function. Okay, so vertex form is called vertex form because it helps you find the vertex. So I already know where the vertex is. All right, so my vertex is at -3, -2. Always the opposite of that sign for the x value of your vertex. Okay, y-intercept was where I would go next. Y-intercept is where x equals 0. So the y-intercept would be f of 0, which is equal to 2 times 3 squared minus 2. Notice I got 3 here because I plugged a 0 in for x. It's going to be another large number. It's going to be 18 minus 2, which is 16. So f of 0 is equal to 16. That's our y-intercept. Okay, so planning ahead a little bit here. Of course, this opens upward because a is positive. I'm going to go -3. So 1, 2, 3, -2. 1, 2. Here's our vertex. Okay, our x-intercepts, how would we find those? Well, what I would do is I would figure out where this equals 0. Okay, so that means I would add 2. So I get 2 equals 2, x plus 3 squared, divide by 2, so that means 1 equals x plus 3 squared. Then I would take the square root, which would get me plus or minus 1 is equal to x plus 3. And then I would add, or excuse me, subtract 3. So my x-intercepts would be 1 minus 3 and -1 minus 3. So it looks like I would get x equals -2, and I would get x equals -4. All right, so x-intercepts of -4, 0, and -2, 0. Let's graph this thing. Do it in yellow, why not? Okay, this is again going to be a poor sketch. Try this again. This will be a little better. Yeah, that'll be a little better. Of course, I'll label my y-intercept 0, 16. Okay, cool. One more example, and then I'm going to have a separate video, you guys, on how to convert from standard or factored into vertex form. Okay, vertex form obviously is very powerful. It helps you find that min or max value, which is more important in the application world. So let's go ahead and do this last example. If you want to, go ahead and pause the video and try it yourself. Okay, vertex in this case will be -1, 3. Let's plot that. -1, comma 1, 2, 3. I'm changing the scale here. It's going to open downwards, so that'll be the max value. And honestly, right now, what I could do is I could find 2 more points using the pattern of change, but I'm going to go along with my instructions here and find the y-intercept. The y-intercept is where x equals 0, so g of 0 would equal -4 times 1 squared plus 3. So it looks like my y-intercept g of 0 would equal -1. Okay, so I'm going to plot that. There's 0, -1. My x-intercepts are going to be nasty. You'll see that in just a second. But what I do know, actually, this is kind of cool. I do know that since this function is symmetrical about its axis of symmetry, which is at x equals -1, I know that this point, this y-intercept, would have a mirror image across that axis of symmetry. So I could sketch the graph, and I could be done there if it only asked for 3 points and the graph. But I'll go -2, -1. But since I asked for the x-intercepts, I suppose I gotta follow through here. Okay, that would be sufficient, though, if it just asked you for 3 points and the graph of the function. Okay, but let's find those x-intercepts. So I would set g of x equal to 0, which is negative 4x plus 1 squared plus 3. Subtract 3 and divide by negative 4. So that would be 3/4 negative over a negative, right? X plus 1 quantity squared. Square root of that, that's going to be kind of yucky, but that would be plus or minus the square root of 3 over the square root of 4, which is 2. So what I'm going to get is root 3 minus 1, gross, or, actually, and, root 3 over 2 minus 1, and negative root 3 over 2 minus 1. So this one will be this point, which will be really, really close to 0. And we'll call it x1, comma 0. And then this one will be x2, which will be further away from 0. Okay, so that would be how we graph using vertex form, finding x-intercepts, y-intercepts, and all that good stuff. Okay. I'll come back again with another video with what's called completing the square. And other than that, hope you enjoyed the video and that it made sense. Shoot me a message if anything didn't quite hit home, and we'll talk then. Have a great day.